substituent on carbon chain 3. Okay, so identify. If you go this way, you get 5. You go that way, you get 5. But 1, 2, 3, 4, 5, 6. So that would be the longest, and this becomes the substituent. Okay, so the substituent is named first, and of course this having meter group on this, the longest one, C. Okay, so that whole thing is named, but put into brackets. Then your position for the carbon is also shown. Then the name for the longest one follows. Right, so let's look at this example and see how we name this one. So let's see how we name this one. The first one says longest chain. So let's go the longest chain. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. It can be. So the longest chain is this. This is the longest chain. And of course, if we go this way, for this functional group will not be in it. So a chain that will contain the most important functional group. Okay. Right. So the functional group alkane. So alkene and alkyne. They are in that order. Okay, so now this is what we have. Right, so let's see how we're going to name it. Okay, so let's see. If we number from here 1, 2, 3, 4, 5, 6. Okay, this will give the lowest numbers to D. So these are the substituents. These are the substituents. Okay, the lowest number 3 and 4. But let's, if you count from here, get this one, this functional group, this precedes. Okay, so this one, it's better to count from here so that we get this one for the functional group, the lowest, as 3 here and then 4 here. If you count from here, then of course we are leaving out the alkyne group is also there. That will not affect it. So after doing that, what are we going to get for this one? Let's see. Right, so let's see. Now, if we count from here, 1, 2, 3, 4, 5, 6. Okay, so let's see which will be better to go. This is giving bromine 4 and giving metal 3. That is going this way. If you count this way, it's giving bromine 3 and giving metal 4. So which one should we go for? Remember the functional groups. Alkene is considered to be greater than E, considered to be greater than I. Okay, in that order. So it means you must give preference to the alkene here, so that it will get the lowest number. Okay. If you count from here, you are giving the alkyne the lowest number. But if you count from here, you are giving the alkene, which should be greater, which is considered to be better, to be ahead of alkyne, the lowest number. So we are better off counting from here. In that case, going that way, this way is the correct way to go, right? But not that way. And then this is 3 bonds, 2 bonds. This one is considered to be ahead of this in terms of the nomenclature, right? Okay. But first, when you are choosing your functional group, make sure when you are choosing your longest chain, make sure your functional groups of importance, those with much importance, are considered in the functional group, are in the longest chain that you've chosen, right? Good. So how are we going to name it now? So we now have 3 for metal and 4 for bromine. So we have what? 3 metal, and then we have what? 4 bromine, and then we have the parent. This thing has what? This 1, 2, 3, 4, 5. So 6. 6 is what? X what? The in is what? Is on position what? 1. So X1 in, and then the ion is in what position? What? 5. 5 ion. Good. I think this will be a good example so that we get all the factors coming into play here. So finally, what will you say then? So putting all together, what are we going to get? So we have 3 meter, 4 bromo, hex 1 in, 5 ion. Okay. So what are we going to get then? Okay. Of course, when we said when you are writing the names alphabetical, the names are supposed to be in alphabetical order. Okay. Right. But in numbering, the one with the functional group considered to be ahead of the other gets the lowest what call it, number. So lowest number is always the okay, alphabetical order. okay, and then substitute. So longest chain, for you to remember, longest chain, lowest number, alphabetical number. So LLA, okay. These three should guide you. LLA, lowest chain, longest chain, lowest number, alphabetical order. Okay. In dealing with alphabetical order, we said we don't deal with the tri, di are not considered. Okay, but the myth, if are considered. So here alphabetical order. This myth, this group, B comes before M. So we're going to get what? 4 bromo, and the number and then between the number and the name just comes. So 4 bromo. 3 meter. 4 bromo 3 meter X. Sorry, X 1 in 5 I. Okay, that's the name. Right, so can check again. Right, so that's, I think this is a good example which has we tried to capture all the various groups. Okay, so that is an example that we use. All right, so that is it. Let's move on to the next. So if you have functional group like this, so this is the alkanoic acid. Alkanoic acid. This is the alkanoic derivative. We are adding this one, so this is actually called the ester. Okay, or alkanoic anhydride. Ester or alkanoic anhydride. So usually the reactions, this is where the bond is broken. Then you have minus here and you have plus here. So the positive here, negative here. So the positive will go with the negative, and then the negative will go with the positive. Okay. So this is an acid and salt. So it will react in that way. So here the positive is here, the negative is here. If this one is going to be split, if this one is going to be broken, then this is going to react with the sodium to form sodium alkanoic acid. Okay. And then this goes with the OH to form another acid, alkanoic acid. Okay. Usually this is kind of a reaction that is what we're discussing when it comes to making soap. Okay. When it comes to making soap, we'll look at that. So the reactions, you look at the functional groups to tell what kind of reaction will be going on. Right. Right. So what will be the name for this one? The longest chain with the functional group. So longest, LLA, longest, lowest number, alphabetical. So longest chain with functional group will be this one. This is the functional group. So this, what kind of functional group is this? The alkanoic functional group. Alkanoic. Okay, it's not alkanoic. Okay. So here, and then when you have done that, we count giving the substituents. These are the substituents. The lowest number. If you count from this 1, 2, we're going to give the functional group a bigger number. We want it to be the lowest, so we should count from here. 1, 2, 3. Okay. So it means we have what? 3 chloro, and then we have what? 2 bromo as the substituent. And then the parent, this thing is what? 1, 2, 3, 4. So butane, because it is butane, 1, or you will not say, so you can just say butanoic acid. Okay. So in that case, we're going to have, which one is going to come first? Alphabetical order. So where is it? Bromo is 2. Chloro is what? 3. So 2 bromo, 3 chloro, butanoic acid. Okay? Right. One thing I also want us to take notice, if you have a compound like this, okay, let's say bromine here, this we can consider as what? Cis. You can also turn it like that. Let's say here, C, and here becomes the bromine. In this case, it becomes trans. Okay, opposite side. Okay, when they are on the same side, it's cis. When they are opposite side, it's trans. Okay, that's something that you may come across. And so we are just picking the little bits that we discussed. and then we'll discuss them. Okay, right. So that is the name for this one as also be discussed. Butanoic acid. So this is what? 3 chloro. We have 3 chloro, and then this one is 2, so 2 bromo, and then the parent name is what? Butanoic acid. Butanoic acid. Okay, right. So putting all together is what? 2 bromo. Between name, number and name is dash 2 bromo dash 3 chloro. Then name to name, so there's nothing there. Butanoic acid. Okay, so that's the name. Right, let's go on to the next one. Alright, so it will be 2, though you may not see it. Let me write it on top so that you see it here. I'll put it here. So 2 bromo 3 chloro, alphabetical order. Chloro. Then you bring out parent name, add it, okay? Butanoic acid, okay? I think now you can see it better. So let's look at the next example. So that's the final answer. Let's go to the next example. Let's see this one. So here, the longest chain, with the functional group, okay? So this can be the longest chain. Somebody will also say this is the longest chain. It's the same thing. If you put whichever way you go. So this is the longest chain. Then when you have done that, you must count that such that the functional group gets the lowest number. If you count from here to be 3. 1, 2, 3, 4. So this should be wrong, but let's see. 1, 2. It gets the lowest number here. So it's better to go that way. To go this way. Okay. 3, 4. So this way. Okay. So the substituent to become the substituent is what? This one, C here. Okay. So let me draw it proper. Here, C. So this 1, 2, 3, 4. This is the substituent now. So we're going to get what? 2 methyl. Okay. This is a functional, so it's not a substituent. So the name of them can how many? 1, 2, 3, 4. So 2 methyl. Butanol. So butan. What's the position of the OH? 2. 2 methyl butan 2 or. Okay, 2 methyl butan 2 or somebody will say 2 methyl 2 butanol. Right? Right, so any of them is correct, you can make it. So this one is showing the position of the O group. Right, so let's move on. Let's get another example. So let's see this one. How are you going to name it? The longest chain. LLA. Longest chain, lowest number, alphabetical order. The longest chain. Somebody will say it is this one, which is the longest chain. And this is just one. Okay, but this is wrong. Why? The functional group must contain a functional group. Okay, this will not be the functional group. This is the functional group we have. So the longest chain must contain a functional group. So this becomes the longest chain. Once this is the longest chain, and this is the molecule itself, this becomes a substituent. So you must note that. So what are you going to get? Functional group. This is ether, so it's an ether functional ether substituent. Okay, it is not on any number, so you're not going to put any number there. And this is what? 1 carbon chain. So ether. Okay, because it is not added to it, will not separate. Okay, separate that, right? Ether methanoic acid. Ether methanoic acid. Right, let's go on. So let's look at basic terms like simple distillation and then fractional distillation. So with simple distillation, you boil when you boil, it turns into vapor, and the vapor is condensed in the column, and then it forms the liquid. Okay, so that's simple distillation. But in fractional distillation, usually you have a column. Okay, so there's a collection. The mixture that you have, the mixture of liquids that you have, they have close boiling points. Okay, they are close. Okay, so as you heat, the first one evaporates. Then within a short time, then second one also evaporates. But as they go up, the place is cooler. Then they condense. Okay, they condense as they come back into the liquid state. Now, as they condense, more vapor will be coming up. So more vapor will heat them up again, so that the one which has the lower boiling point rises again, and then within some time the second one will also rise, but they will meet another cooler point, and then they will condense. So this will go on until at the highest point you have more of the one which is easily evaporated. Okay, the one with the lowest boiling point at the higher column than the other one. So in that case, you have separated the two mixtures. Okay, so this is the fractional distillation. So for fractional distillation, they must have close boiling points. Okay, and that is what happens. Simple distillation is what we get. Just vaporize, condense, that means change it back to water, and then collect it. Okay, that's simple distillation. This is used in the petrochemical industry. Right. Chromatography. So chromatography. So this is a means of separating mixtures, okay, or purifying mixtures, okay. So what happens is you can have a solid phase. This can be solid or stationary phase. Okay. Okay, so the mixture, that the one that you want to separate, is added onto the surface. Okay, but because this one has some attraction for it, the movement in the mixture will be different. Okay, and because it's different, to some degree there will be separation at the end. Okay, so this one is, they are absorbed or absorbed to the surface. Okay, so that means they get adhered to the surface. So the way, depending on the attraction between this surface and then the molecule, if it is greater, it will not be able to move faster. The one which is weaker will move more. So at the end, you have some here, some there. This one may be the one which is more attracted to the surface, less attracted. So in that case, you have separated them by chromatography. So this is one way. This is what we call the absorption what? Chromatography. There's another one where you have the solid phase and then you have the liquid phase. Okay. So the mixture is going, but the one is more readily dissolves in this one, the other dissolves in this one. Okay, so depending on the degree in which one dissolves, they will all move, but at different phases between the two. So this will be the mobile, this will be the solid or stationary phase. Okay, but because of the different movement of the component of this mixture between the two phases, the mixtures can be separated. Right. So what is happening is, so as this one, there is a stationary, one, there is a mover. Okay, the mover faces, the water is moving, and we have the mixture here. As the water moves over this, to some degree, the component of this one may be more soluble in the liquid one than its adhesion to the solid phase. If it's more soluble in water, then water will wash it off. And then if it is more adhered to this one, water will not be able to wash it off. So at the end, you separate the component of this mixture. So this is what we call the partition chromatography. Okay? Right. Right, so let's also look at when we talk about the transition element, ion 3 plus, yes, okay, because the electrons can move. If you have this, the electrons can move from one state to another, okay. When they move, they absorb it. When they absorb energy, they move, and then when they are returning, they release that energy, depending on the wavelength of that photon, okay. Usually you may have colors, the compound will give you colors, okay, as in the case of blue or some shades of red or brown, in this case, in these two cases that we have, okay. So depending, copper may also come with different colors, okay. So these are the transition elements. The distance, the energy level between the 3D and then the 4S, which is here the D, they are close, so they can move up and down. They can be excited, they go up and then de-excite and come to the ground state, releasing the energy they absorb. And then the energy that is released, if it has a particular wavelength, and then frequency, which will correspond to a certain color, then our eyes will detect that. Of course, our eyes has cones and then rods, okay? The rods are for black and white picture, the cones are for C, color picture, okay? So we have three of them: red, blue, and what? Green, okay? These three colors, okay? Red, blue, and green, okay? Right, so these three colors will be combining to give us the shades, different shades of colors. Right, so depending on the wavelength coming in, to excite one of them at the column, okay, different ones will excite them, and then a picture of that substance will be seen. But remember, if you are talking about the color shades, if you have red here, say green here, then you have blue here, okay? Red, this, you can use this one to remember. Red, gold, green, okay? This is our Ghana flag, okay? It's red, gold, green, okay? Then we have the BCG. For BCG is Basil Camet Guerin. It's the vaccine that is used against TB, okay? BCG. So here too we have G and we have B here, so C, okay? So this C is a sign, okay? That's a color. And of course, the other color left to be magenta. Okay, so these shades of colors, when you have all the colors coming together, then you have what? White. Okay, so just three rods will be able to tell, depending on which one will be excited, that part of color will be what will be excited, and then it will go from, that is within the antenna. These are within the retina. From the retina, it will go through the optic nerve to the visual cortex, and then the brain will process it through the primary, secondary, and tertiary phases, okay, and then give you an interpretation of the color. But remember, the eyes, like we said, the lens of the eyes is very good at has this chromatic aberration. It's adapted to dealing with chromatic aberration. It means it's usually with separate colors. By separating, it is able to tell the exact color of the object you are seeing. Okay, and that is how our eyes have been designed, adapted to do. Right. So as we do this, I'll always be bringing other fields in so that we can link them and then be able to make sense of what we are dealing with. So this is just a small diversion. Let's go back to our chemistry, organic chemistry, right? What we call isomerism. Isomerism, okay? So when you talk about isomerism, it means having a variety of the same thing, okay? So let's say we have this. I can also write it like that. Okay, so these are isomers. So based on isomerism, you can have what we call the structural isomers, or we can have what we call the stereo isomers. Okay, so structural isomers, it means they have the same what do you call it, structure, but different positions. Okay, it can be the position which is different, or different functional groups. Okay, different functional groups. Okay, different functional groups. So either the position is changed. So you see that this one, the position has been changed. So although the structure, they have the same structure, but the position has changed. Okay, so they have the same structure, but same different position. Now the stereo isomers, we have what we call, you can have the geometric isomers or the optical isomers. Okay, right. So we'll look at, so this is an example of the structure. So we're just changing the position. Okay. Now when it comes to geometric isomers, stereo isomers, these ones, what happens is they have the same structure. Okay, they are the same in terms of structure, and then let's say the point is let me use an example here. Geometric, let's say this is ER, or let me make it C, or let's put this X, let me put X here. X can be any halogen, there's another X, okay? Right, so this is it. Now see, this one has the same structure, but you can have it like that. You can just turn it this way. So you see the same structure, but the same, the orientation has been changed in space. So they have the same structure, but orientation in space is what changed. That will be stereo isomers. So space, there's difference in the space orientation. Orientation is how they are organized in space. Okay, that is what is going to change. So this one, where they are on the same side, we say it's cis. When they are on the side, we say it's trans. Okay, so this will be cis. Let's say it is bromo, cis 1, 2 dibromo, ethane. Okay, ethene, sorry, ethene, 1, 2 dibromo, ethene. So that is under, so this will fall under the geometrical isomers. Okay, now let's look at the optical isomers. The optical isomers, they are more or less mirror images. Okay, so mirror images, let's say let's say this is the mirror. Then I'm going to get ER here. See. So for instance, you see that this one and this, they are mirror images. Okay, optical isomers. So optical is referring to optics, lens and mirrors and so on. So they are mirror images. Okay, right. So you see that this and this, if you are bringing them together, they look alike. Okay? But if you are putting this one on this, you cannot superimpose this one on this one, no matter how you do it. Okay, you'll not be able to superimpose this one and have the orientation being the same. So they are mirror images. In terms of mirror images, they are mirror images, but we cannot superimpose one on the other. In that case, they become what we call optical isomers. They become what we call optical isomers. Okay, they become optical isomers. So sometimes it depends on the rotation. So depending on dextro rotation, dextro rotation, that is in the direction of the right. Okay, and then the level, etc., the opposite, and so on. Okay, so that will be under optical isomers. Right. Right. So let's look at a free radical. Here, this is the bond between carbon and this. This bond can break, and then you can have what? C with one electron in it. Okay, it's not charged, but it has one electron in it, and then Cl also have one electron in it. So this is a free radical, this is a free radical. These are very highly reactive. They can abstract or take atoms from other compounds in a reaction. Okay, this can provoke, if you have this one, let's say you have more chlorine in here, this can go on. If you have another one here, it can abstract, take one hydrogen here, so that at the end you have this with maybe chlorine, another chlorine, until you have chlorine saturating all the point. Okay, through this chain reaction of free radicals. Okay, so once you have free radicals, they can take So this one, if free radical, there's a H here. This can take it, so that it form hydrogen chloride, and then it will left with this. So that another chlorine will add here. Chlorine will add here. So this can go on to generate this tetrachloro methane kind of compound. Okay, so free radical is what I want to illustrate. Okay, that's a bond with electron which is not paired, but very highly active, ready to pair. Okay. Now let's look at this bond. Now sometimes you can have, let's say, let me put bromine here. It is -1. That's bromine ion, okay, or anion. That's a bromine anion. Now remember that we said C and oxygen, they are not the same. So in terms of pulling electrons, okay, the way the electronegativity of oxygen is not the same as this. So oxygen will pull more of the electrons being shared onto itself. So this electron is to be pulling more onto this one, to the point that sometimes it can become this minus, okay, or as like this here, okay. When it happens that way, it will make this one positive. So this carbon becomes a carbocation or positive cation, okay. So when it happens this way, if there's a nearby anion, it can react with this one. It can combine with this. By coming together, it will displace this one, okay, so that this will move, and then you can have what COBr forming, okay. So this one which has been made positive, okay, and this is which is a -1 coming. This is a nucleophile, okay, that's what you have here. Okay, it is going to what we call the electrophile. The electrophile means love for electrons. So this one wants electrons, and this one wants the positive side, the nucleus, which contains protons. So nucleophile. Phile means like, okay, like. Okay, so electrophile is the positive one. It wants electrons, so it's attracting. The two can come together to react, and usually this is how organic reactions go on. Okay, so there's a partial positive or negative displacement. So this is becoming negative, this is becoming positive, and this goes up. By doing so, if it is becoming negative, partially positive, if this one comes, it may help by pushing, by bringing it negative here. It may help this one to take the electron. So this already wants to take the electron, but that somebody is providing it with another electron. So it come and bond with this, leaving this electron, and then you have it here, okay? And then a new compound before, okay? So resonance, that is movement of the electrons. Nucleophile is a -1. Electrophile is a +1, okay? And then the movement of the electrons. Sometimes to get a positive charge or negative charge,